The proof fixes a communication protocol that for every input valuation pair V1, V2 finds an optimal allocation as complement. We will construct a following set, a set of valuation pairs with the property that the communication patterns produced by the protocol must be different for different valuation pairs. Specifically, for every 0 or 1 valuation V, we define the dual valuation V star to be V star of S equals to 1 minus V of S complement. Note that 1, V star is indeed a monotone 0 or 1 valuation. And 2, for every partition S complement, and S which is a subset equals to M, we have that V of S plus V star of S complement equals to 1. Lemma 11.26. Let V not equals to U be arbitrary 0 or 1 valuations. Then, in a welfare maximizing combinatorial auction, the sequence of bits transmitted on inputs V star is not identical to the sequence of bits transmitted on inputs U star. Before you prove the lemma, let us see how the main theorem is implied. Since different input valuation pairs lead to different communication sequences, we see that the total possible number of the communication sequences produced by the protocol is at least the number of valuation pairs V star, which is exactly the number of distinct 0 or 1 valuation V. The number of 0 or 1 valuations can be easily bounded from below by 2 to the M choose M over 2 by counting all valuations such that V of S equals to 0 for all S whose size is less than M over 2. V of S equals to 1 for all S whose size is greater than M over 2, and allowing V of S to be either 0 or 1 if the size of S is exactly M over 2. There are M choose M over 2 sets of size M over 2, so the total number of such valuations is exponential in this number. The protocol must thus be able to produce 2 to the M choose M over 2 different communication sequences. Since these are binary sequences, at least one of the sequences must be of length at least M choose M over 2. Proof. Assume by way of a contradiction that the communication sequence on V star is the same as on U star. We first show that the same communication sequence would also be produced for V star and for U star. Consider the case of V star, i.e. Alice has valuation V and Bob has a valuation U star. Alice does not see U star, so she behaves and communicates exactly as she would in the V star case. Similarly, Bob behaves as he would in the U star case, since the communication sequences in the V star and the U star cases are the same. Neither Alice nor Bob ever notices a deviation from this common sequence, and thus never deviate themselves. In particular, this common sequence is followed also on the V star case. Thus, the same allocation S as complement is produced by the protocol in all 4 cases: V star, U star, V star, U star. We will show that this is impossible, since a single allocation cannot be optimal for all 4 cases. Since U is not equal to V, we have that for some set T, V of T is not equal to U of T. Without a loss of a generality, V of T equals to 1 and U of T equals to 0, and so V of T plus U star of a T complement equals to 2. The allocation S complement produced by the protocol must be optimal on the valuation pair V U star, thus V of S plus U star of S complement is greater than or equal to 2. However, since V of S plus V star of S complement plus U of S plus U star of complement equals to 1 plus 1 equals to 2, we get that U of S plus V star of S complement is less than or equal to 0. Thus, S complement is not an optimal allocation for the input pair U V star, contradiction to the fact that the protocol produces it as the output in this case as well. More complex lower bounds on communication allow us to prove tight lower bounds for iterative functions in various settings. The above lower bound on communication can be extended to even approximating the social welfare. Theorem 11.27, for every epsilon greater than 0, approximating the social welfare in a combinatorial option to within a factor strictly smaller than the minima chosen between either n or n to the 1/2 minus epsilon, requires exponential communication. Note that this is tight. Achieving a factor of n is always trivial by bundling all items together and selling them in a single item auction. And for n which is greater than or equal to the square root of m, there exists an big O of square root of m approximation. See figure 11.5.2. Actually, most of the lower bounds described in figure 11.5.2 are communication complexity results.